Okay, welcome back to the C++ course. This is chapter 19, a chapter all about stacks and queues. So last chapter we discussed a particular data structure called a linked list. Stacks and queues are more specific types of data structures. They're sort of, you could think of them as kind of like linked lists, but with some additional restrictions placed on them. And there's very good reasons to place restrictions on data structures. One of those reasons is if you restrict how they work, in some sense you can provide some sort of guarantee about how fast or slow the data structures will perform on small to large data sets. That's exactly what stacks and queues are. So let's take a look at our objectives today. So we're going to introduce stacks, talk about them conceptually, try to paint a picture of them using terminology that hopefully you're already familiar with. Talk about dynamic stacks. We'll look at the STL version of a stack. Similarly for queues, talk about them conceptually first, maybe draw some analogies. We'll talk about dynamic queues, and we'll take a peek at what the STL provides as far as dequeue and queue containers. And then we'll talk a little bit about how to eliminate recursion in our data structures. All right, introduction to stacks. So a stack is something called an LIFO. A lot of times people will say LIFO, and that stands for last in, first out data structure. This is a term, LIFO, that you may have heard in everyday life as well. This can apply to just different things in your day-to-day routine. If something is the last in, it is the first to come out. Good examples, sort of some classic examples, are plates in a cafeteria serving area. If you think about a stack of plates when you're going through like a line in a lunchroom, there's a stack of plates where the bottom of the stack, say the dishwasher brings out a stack of plates, they're clean. He puts the stack on top of the stack that's already there, waiting for people to pick them up. So the stack gets put on the stack of plates that's already there. When a person goes through the line, they take one off the top. So it is the last one that was put in, so last in, and it is the first to go out when it is needed. Similarly, return addresses for function calls, so directly related to programming. When we have a function that is last in, it is the first to come out. So if we get like 5 function calls deep, when we return from those function calls, we return from the last function that was called and we work our way back. There's another example of this in your computer or your web browser. As you're navigating from page to page, surfing the internet, when you go back, we're actually navigating a stack data structure. So the last page that we're visiting, like this page, if I hit back, it would be the first to go away, and I would make my way back up the stack. So lots of good analogies to draw here. Oh, I should mention too, I did neglect to put in the page numbers and things for the hands-on exercises, so I apologize in advance if that's a little rough. I'll be jumping back and forth like always between the exercises in the textbook and the PowerPoint. So again, I apologize if those transitions aren't maybe as smooth as they used to be. Here's a good diagram though of a stack. Picture again a stack of plates in a restaurant or at a buffet or something. So it's a stack like this. The 5 plate is the last plate that is put in, so it'll be the last plate that comes out. If we put another stack on top of that, the plate on the very top of that stack will be the last one to come out. Yeah, there are some stack operations. They're called push and pop. They put things onto the stack and pop things off of the stack. And it's usually implemented with a list with with additions and removals taking place at one end of the list. The active end of the list implementing the stack is called the top of the stack. And kind of like arrays and different data structures, there's a static stack, which is fixed size, implemented using an array, and then a dynamic stack, which you can implement using a linked list, where the size would vary as needed, and then we just use like nodes and pointers like in a linked list. Operations. So we have really 2 big operations here when you talk about stacks. We can push items or values to the top of the stack, and we can remove values from the top of the stack. And notice how both of these operations are dealing with the top of the pile, the top of the stack. Pushing items on, popping items off. Then we have some maybe utility functions like isEmpty, which returns true if the stack currently contains no elements at all. So here we have a static stack, which uses an array of fixed size. The bottom of the stack is index 0, and a variable called top tracks the current top of the stack. So constant stack size, good constant, size is 3. We have an array of chars of size stack size, and the top is going to be 0 because we don't have anything in it yet. So the top is 0 also would mean, take that to mean as the stack is actually empty. So again, some operations using an array. So the stack has a max capacity of 3. Initially the top is 0 and the stack is empty. So remember, this is an array of chars. So if we push the letter E, now E is at the top of the stack. So that little property top is now 1. Sorry, over here. Top is now 1. If we push on to K, K goes on top of E. The top is now 2, and we push on G. Now the top is 3, and we've reached our max capacity. Some more operations. After 3 pops, top is 0, and the stack is empty. So kind of continuing where we left off in this previous slide, we had GKE. If we pop, notice actually when we push, we have to push a specific piece of data, but when we pop, we don't have any inputs. When we pop off the top of the stack, we're removing G, we're left with K and E. Pop again, we're left with E. Pop again, we remove E, and we're left with nothing. Now, some stack implementations, when they pop, they truly just pop an item off the stack and that's it. There's no return value. Other implementations, when you pop something off the stack, it would actually return the thing that was popped. So I think the top of the stack was the letter G. So if I called pop on this stack, I would actually get the letter G back. Other stack implementations have something like a peek, where you can peek at the top of the stack to see what value is actually stored there. Let's see if we have a hands-on related to this. And perhaps since we're more or less familiar with a lot of this code, to be honest, there's not a whole lot new here in this chapter. We're really just kind of using what we know and, again, putting some restrictions on it. So perhaps we'll just talk through some of the code examples, and you guys can feel free to pause at any point and type them in yourself if you would so desire. So here's an example of an int stack contained in a single header file. And it looks like they're utilizing classes. So let's jump ahead one slide here and take a look at the class implementation of using an array for our stack. So we have a class called stack. For some reason it's capitalized. I'm not sure why. All right. So we have a unique pointer to char called s that's going to serve as our kind of, I should mention that we call this the backing data structure. So we call the data structure a stack, but behind the scenes, there still has to be something like concrete built into the C++ language that we use to contain the elements of our data structure. And in this case, and we call that the backing data structure. And in this case, we're utilizing a pointer to char called s, and it happens to be an array of pointers to char. So that's going to be our backing data structure. We have an int called capacity, how big can it be, and basically the top of the stack. So of course we have public methods void push, which pushes something onto the stack, void pop, which pops something off the top of the stack. We have an isEmpty, we have a constructor here which accepts an integer for the capacity, and we have our destructor. Let's see, over here in the int stack implementation, kind of the same type of thing here, except for the stack exceptions. So they are building into this implementation of a stack, essentially from error checking. If you remember back from the chapter on exceptions, that was bundled with exceptions and templates, that lesson, we had some we talked about some customized exceptions, and this is what they're trying to do here. I can't tell you right off the top of my head what over and underflow are going to do, but we shall find out soon enough. Those exceptions are left off of this stack implementation, I believe. Oh, here they are. So we use the stack exception classes as members of the stack class to signal that an underflow or an overflow exception has occurred. And again, we'll see hopefully what those look like in a minute. So checking to see if the stack is empty, that is a Boolean method, of course, so returns true or false. Is empty will simply return if our member variable top is equal to 0. If it's equal to 0, that means it's empty. I should point out this is shorthand syntax. I hope that you're comfortable with this by now at this point in the course. We could have an if statement saying if top equals 0, return true, else return false. All of that is actually bundled into this little piece of syntax here. We're returning if top is equal to 0. So that's going to return true or false corresponding with our bool return type here. Pushing on to the stack then. So we push a char x. Okay, here's our overflow exception, so this is good. If we try to push a char x on top of a stack that is already at capacity, we're going to throw that custom exception that we kind of defined in our header file. So we're going to throw that overflow. It's overflowing with data, you can think of it that way, if we try to push something onto a stack that's already full. Otherwise, we're going to keep going and just say the array s at location top is going to be equal to whatever char x we passed into the push function. Then, of course, we're going to keep track of that top property as we push things onto the stack and remove things from the stack. Likewise, when we're popping, we're not returning anything. I'm not sure. Let me advance a few pages here in the book. I'm a little confused about something. Removes a value from the stack and returns it. Oh, okay. Yeah, because this is that, yes, we are passing in by reference here, so that makes sense. Okay, let me break this down. That looked a little strange to me. I would have expected to see the char here to return it after you've popped it off the stack, but this works too. First of all, if the stack already is empty, there's nothing to pop. So we're going to throw our custom exception called underflow. So we have overflow if it's full, underflow if it's empty. Hopefully that makes sense. Otherwise, we'll keep on chugging here and say top minus minus. So we're keeping kind of a running track of what that top is. And then we're going to say x is equal to s at location top. So remember, and again, this is a little strange to me. I'm not used to seeing a stack implementation like this, but when we pop, in this case, we're going to have to pass in a char by reference that's going to have a value after pop finishes. So what is that by reference x going to be equal to? It's going to be equal to whatever the thing at the top of the stack is. So s at location top. I hope that makes sense. If it doesn't, take a look back at the pointers chapter and see if that will help you kind of clear up any confusion about how we're actually like returning a value from popping it off of the stack. Passing it by reference, setting it, assigning it to s at location top, and then after we return from the pop method, we will then have this value stored in whatever char we passed in by reference to the pop method. Hope that makes sense. Okay, so the exceptions. So the preceding examples use exception classes to handle cases where an attempt is made to push onto a full stack, which is overflow, or to pop from an empty stack. In that case, underflow. So programs that use push and pop should do so within a try block and a catch block. So we say try catch. Remember back from that lesson, the catch block should follow the try block to interpret what occurred and then inform the user. Let's make sure we're caught up here on the textbook side. Good, here we go. So we're going to use that int stack.h. And in this case, I'm noticing that they're not actually trying and catching, as the slide said, but we are including int stack.h. We're creating a new stack of size 5, assigning it some values, have a little local variable here called value. We're going to push onto the stack values from 0 to 4. So while k is less than 5, we're just going to say stack.push values at k. And I misspoke earlier. This is a local array that we're using to store these values, and we're just pushing them onto the stack by looping through it. Then we're going to pop off of it. So while not stack is empty, or you could say while stack.isEmpty equals false, we're going to say stack.pop and pass in that value. We see out the value, see out an endl, and a return. So we're pushing on and then popping off. So it's like forwards and then backwards. Here's another good example. Feel free to pause the video here and see and make sure you can follow this as we push things on to a full stack and then pop things off of the stack. Okay, here's a little section on handling stack exceptions that we just talked about. Good. So this is the same example, 19-2, only here we are utilizing the try catch. And if you remember from the implementation, where we're actually doing the throwing for underflow or overflow is in the push and in the pop methods in the class. So we're throwing them there, but we're checking for them in this try catch from int main. So notice we're going through doing our stuff. In the case that we do have an overflow, we're going to catch it here and then print out sort of a customized error message. And if you follow this example through, you will see we're basically like forcing an overflow exception just to kind of see how it works. Cool. And then of course, you know, we talked about int stacks. You should ideally templatize the stack so that it can use any data type. And it's, left as a programming challenge. If you care to do that on your own at the end of the chapter, would be a good exercise to try to convert that int stack into a template stack of type T. Dynamic stacks. So the storage for a stack can be implemented as a linked list, and that explains why we kind of had to cover that chapter last time before we made it to the stacks and queues chapter. No need to indicate the initial capacity. It can grow and shrink as needed and can never ever be full, caveat, as long as the memory is available. So as long as your computer has enough memory to accommodate your very, very large, potentially dynamic stack, you're good to go. We don't need to necessarily check for it. So there's no need to test for an overflow there. We can still check for an underflow because it's possible that we would still be trying to pop off of an empty stack. So here we go. And if you notice here, we're kind of building on previous chapters now. So we do need to have some class that represents a dynamic linked list. So that's going to be, instead of an array as our backing data store, we are now going to have a linked list as our backing data store. And so within the class, we define a private data member class called LNode for dynamic nodes in the list. And we define a node pointer to the beginning of the linked list, which will serve as the top of the stack. So instead of like keeping an int, having an int that keeps track of the top of the stack, here we're going to have a node pointer that will tell us where the top of the stack is, and we'll have to move that around. We'll have to move that pointer around as we push on and pop off of the stack. So here could be an example of some operations. So we could have the top here pointing to three push operations. Oh, right. After three push operations. So top initially is pointing to nothing. We push A. We have A over here. We push B on top of that and push C on top of that. And now top is pointing to C. It looks a little strange kind of horizontally. Usually you see stacks and queues listed vertically because we talk about the top of the stack. But in this case, the left is kind of the top, where our top pointer is pointing to the last thing that was pushed onto the stack. Still, we have the is empty. Instead of checking to see if top is 0, we're now checking to see if top is equal to the null pointer. Pretty straightforward. When we push things onto the stack, we push a char, and now top is equal to a new something called an L node, which presumably is defined in your linked list class. A new node, a new linked list node, where we're passing in the data piece x and the pointer to the next node top. We want to remove. So we're still doing that funky syntax where we're passing in a reference to a char, and that will eventually store the value that was popped off of the stack. So we're going to check to see if the stack was empty when we popped. If it is, we're going to say, hey, you can't do that. That's an underflow exception. Otherwise, we're going to say x is equal to top's value. So we're not actually, important note here, we're not actually returning like the node, we're returning the data inside of the node. Then we're saying lnode pointer, old top is equal to the current top. We're going to say top is equal to top's next. That's what does basically the popping. So we're pointing to top's next node, and then we're going to delete the old one to free it up from memory. But keeping in mind that we still have the data from that node stored in our X reference. So how does the STL do this? Let's forward in our book here a little bit. Dynamic int stack. Again, I'll kind of scroll through this slowly if you would like to pause and take a look at this implementation. It's basically the same thing we talked about though, with copious amounts of comments. Let's take a look at the destructor though. That could be interesting. Yeah, so when we destroy or when we delete an int stack, we have a stack node pointer called garbage, and that's pointing to the top. And we're going to say, while garbage is not equal to null, so while it hasn't reached the end of the stack, we're going to say top equals top.next, arrow next, and then say garbage next is equal to null pointer. We'll delete the garbage node and then assign garbage equal to top. Do that over and over again until we have no more nodes to delete. And that is what happens when you say delete the dynamic int stack that I created. Here's another example that would demonstrate that, the dynamic stack. So we have our data here. We have our stack popped value that's going to keep track of whatever values popped off the stack. We're going to push some data onto the stack. We're going to pop 3 values and print out what they were. The stack is now empty. So we're going to try catch here just to kind of prove that the underflow works, and it should definitely work, as you can see in the program output here. Okay, STL stack. So stack template can be implemented using a vector, list, or a dequeue, and it implements a push, pop, and empty member functions. It implements other functions like size, the top, which is a reference to the element on the top of the stack, and you have to use it with pop to remove and retrieve the top element. Container adapters. A little bit of an advanced concept here, but a class that provides a new interface to an existing class is a container adapter. So the purpose is to provide a specialized use of an existing class. Sometimes I would call this idea like a wrapper. So it's a wrapper around an existing container that provides like a new or more straightforward way to use it perhaps, or like a customized way to use it that makes more sense to your particular use case, your particular program. So the STL stack container is using either a vector, a list, or a dequeue as an example of a container adapter. Let's scroll a little bit forward here. Here's the STL stack. So like with most of our data structures, we have to include stack, then we can use it. So we're saying here, check out this, this declaration though. Okay, so we have a stack, that's cool. And I guess we're gonna have a stack of ints, but notice the comma here. I don't know that we've actually seen 2 data types included between the double angle brackets here. So stack, we have a data type int, comma, then we specify what do we want our backing data store to be. We want it to be a vector of ints, and we have another set of angle brackets, which still needs a data type. So a vector of ints is still a data type, and int is certainly a data type, and we're going to call it an I stack. So that's that kind of container adapter idea that the slide was talking about over here. After you're done with that though, you can continue using the stack as you need, pushing and popping, getting the size, etc. But I want you to be really comfortable with this sort of syntax here. This kind of scares people sometimes, seeing the nested angle brackets. Sometimes if you start inward and work your way outward, that makes more sense to people too. So inward, I have a vector of ints as an argument or a parameter to my new stack declaration. Cool. Good. Right. Okay. Defining an STL-based stack. So here's kind of what I just mentioned in the slide format. So defining a stack of char named cstack implemented using a vector. So it's a stack of chars implemented using a vector of chars. Make sure to separate these guys with a comma. Implemented using a list. So I have a stack of chars implemented using a list of chars called cstack. We don't really know what a dequeue is necessarily. We'll get there. But here's an example of that. Implemented using a dequeue, this happens to be the default. So if you just say stack of chars, that's, that is acceptable. You don't have to pass in what your backing data store would be. If you do not, then it's going to be a dequeue by default. Oh, and check this out. Prior to C++11, spaces are required between consecutive angle brackets and symbols to distinguish from stream extraction. What does that mean? Well, think about where else. Let me back up a slide here. Now we can do it here. Where else have we seen that? Okay, cin. Cin also has that. So the idea is to disambiguate. But that's only prior to C++11. So they've made great strides in modern C++ to actually, based on the context that it's used, determine whether or not you're C-inning or if you have a nested set of angle brackets. All right, let's shift gears and talk about queues. So if a stack is a LIFO, a queue is a FIFO, in other words, first in, first out. This, everybody's experienced a queue in their life if you ever have waited in a line for something. If you've waited in line at a fast food restaurant or to go on a Ferris wheel at the amusement park or the roller coaster, if you stood in line, you have stood in a queue. In fact, I'm an American, so I'm used to the term line, but across the pond in Europe, they do actually just use the term queues to describe a line of people waiting for something. So it is first in, first out. If you're the first person in the line, you're going to be the first person out of that line. Example, people waiting to use an automatic teller machine. Cars lined up to pay and exit a parking structure. We have different implementations. We can have static, fixed size, implemented as an array, or dynamic, implemented as a linked list. So queue locations. In a queue, so with the stack we're adding and removing from the top, but the rear of a queue is where we're adding elements. The front of the queue is where elements are removed. And before I go any further, take a minute, pause the video, memorize how to spell the word queue. Q-U-E-U-E. Q-U-E-U-E. You will do well in life if you remember how to spell the word queue. All right, so here's kind of an example diagram. So we have the front of the queue, we have the rear. New things are added to the rear. Things that are removed get taken off from the front. All right, the array implementation. So it is an empty queue that can hold chars. So to push or to put things into the queue, we use the term enqueue. E-N-Q-U-E-U-E. So think about a line of people or cars. If you want to put a new car into the line of cars, you would enqueue the car. And then you'd have a new thing in your line or in your queue. We would enqueue K, so K goes at the rear, E is still at the front. We would enqueue G, G goes at the rear. Notice our front pointer and our rear pointer. To remove is called dequeue, D-E-Q-U-E-U-E. Okay, if we dequeue from the full queue we saw back here, E would be removed and presumably returned somehow from the dequeue method. We would dequeue again, we would be removing K and returning it. And then if we dequeued the G here, we'd be left with the empty queue. Let's scroll forward a little bit here and see if we see everything. Yep, a couple examples, enqueuing some integers in this case. Dequeuing some integers until we're left with the empty list. Empty queue, I should say. Mixed sequence of queue operations. Let me back up one. In the dequeuing operation, reading from the text here, the element at the front of the queue no AI, is removed. This is done by moving all the elements after it forward. So this becomes a little bit of a challenge if we're utilizing the array implementation. And I guess the slides outline it here. So let's just read from the slides. In the preceding example, the front never moves. Whenever DQ is called, all remaining queue entries move up one position, and this move takes time. Okay. The alternate approach, and it does get a little confusing, uses a circular array where front and rear both move when an item is added or removed. Both can sort of wrap around from the end of the array to the front if needed. There are other solutions, including the dynamic queue implementation, but this is one of them. And again, here in the text, notice the problem with this algorithm is that it's inefficient when we're moving the queue entries. It's very inefficient. So with every operation, we have to slide all the entries. Not a big deal if it's just a 3-element queue, but if your queue is like thousands or maybe 1 million elements, then yeah, that's going to take some time. So when we're dealing with the circular array, we're just dealing with pointers, and it kind of looks like this. All we're doing here is moving pointers. The problem with this approach is that the rear index cannot move beyond the last element. Solution is to think of the array as circular instead of linear, and when the item moves past the end of the circular array, it wraps around to the beginning. Cool. For example, consider the queue depicted here. Okay, somehow we ended up with a state where the queue looks like this. Remember, this is a static array implementation. So index 0 has no elements, but index 5 through 8 have elements. The value 3 is the rear of the queue, okay, and 7 is the front. So now suppose an NQ is performed inserting the value 4 into the queue. Well, okay, so if I want to NQ something, I would have to like either draw an imaginary index back here, which is not cool, or talking about the circular nature of this, when I NQ into an array where my rear pointer is at the end of the array, I'll just move my rear pointer and wrap it around to the front, and now my NQ is here. So when this starts happening, you can't really think of like a concrete front and end of the array. Now you're really having to rely on your rear and front pointers to tell you where the front and rear of the array is. So what's the code for wrapping it around? It's not that bad, I guess, but you could say if rear is equal to queue size minus 1, which would be this case, queue size minus 1, rear is then going to be equal to 0, otherwise just increment rear. So that's the algorithm. Another approach looks like this. I don't like this. I don't think this is very readable or intuitive, but rear equals rear plus 1 mod queue size. So detecting full and empty queues with circular arrays. I'll leave this to you guys to kind of digest. The good news is about this, none of this is necessary with the list-based approach because we're not dealing with static arrays. So array implementation issues. So queue variables needed are queue size, some pointer called queue to the int array. We're maintaining a front and a rear pointer defaulted to -1, and then some number called 0, which is how many things are in the queue. These could be members of a queue class, and the queue operations would be member functions, of course. The is empty looks very similar to the stack implementation. If the number is equal to 0, that means it is empty. Is it full? Is the number equal to the queue size? That means it's full. Okay, to NQ, we need to add an item X to the rear of the queue. So the queue convention says queue rear is already occupied. Executing. If not full, rear is equal to rear plus 1 mod queue size. That's this business that we were talking about. Mod operator for wraparound. Yes, again, I prefer to use the non-modulus method. Just make it an if statement. To dequeue, we remove an item from X from the front of the queue. And we say if queue front has already been removed, we execute this. If not empty, front equals the algorithm that we talked about earlier. Okay. So NQ moves the rear to the right as it fills the position of the array, and DQ moves front to the right as it empties. So when NQ gets to the end, it wraps around to the beginning to use the positions that have been emptied, and when DQ gets to the end, it wraps around to the beginning to use the positions that have been filled. Yes, that's not confusing. Just checking here the textbook. Static int Q class. Good. They've added a little clear method that would clear out the contents of our queue. Constructor. Notice how we've initialized to -1. Again, feel free to pause and type if you feel like you need it. I'm not so concerned with syntactical issues now as I am conceptual at this point in the course. Here's using the int Q implementation, enqueuing 5 times, dequeuing and retrieving all the items while it's not empty, going through. So NQ wraps around by executing this, DQ wraps around by executing this. All right, exception handling. So static queues will encounter an error if an attempt is made to NQ an element to a full queue or DQ an element from an empty queue. Better design is to throw an underflow or an overflow exception and allow the programmer to determine how to proceed. To do that, we use try and catch blocks, of course. So like a stack, a queue can be implemented. So with the dynamic queue, of course, we use the linked list, which would allow dynamic sizing and avoid the issue of wrapping indices. That issue alone is enough reason for me to just say always use a dynamic queue, always use the linked list implementation, but your mileage may vary. So we define a class for the dynamic queue. Again, since we're relying on the linked list as our backing data store, we have to have some linked list implementation that we can use and sort of embed in our queue class. So we have a private data member for the dynamic node in the queue, and that node points to the front and rear of the queue. Or sorry, node pointers, plural. So we have a node for the front pointer and a node for the rear pointer. Of course, to detect if it's empty is the front equal to null. That would mean empty, and to add an empty or to add an item at the rear, we would check to see if it's empty. If it is, we say our front is equal to a new queue node that contains some data X. And we would say the rear is equal to the front. So that might look a little funny. So rear and front are both basically pointers. So if they're both pointing at the same thing, you can kind of infer from that basically that the queue has a single element. So that's the special case for if the queue is empty. Otherwise, we're going to say the rear pointer's next node is equal to a new queue node passing in the data X. We're going to say rear is equal to rear's node arrow next. For DQ, for removing, we're going to, again, check to see if it's empty, throw an exception, handle it, leave it up to the user how to handle it. So if it's not empty and we're DQing, we're going to say some value X is equal to the front arrow value. So that's going to be presumably what we return, even though there's no return statement. Effectively, it's what we return back to the user after calling a DQ so they can see the value of the thing, the value of the node that was DQ'd. Then we're going to say a queue node pointer to the old front equals current front. Front is equal to front's next. And then, of course, we're going to delete the old front to clean up after ourselves. And then the STL, so somewhat similar here. STL's implementation for DQ and queue. So a DQ is a double-ended queue, sometimes called a DEQ. It has member functions to NQ pushback and DQ pop front. A queue container is so here's a term we haven't encountered before, but we've been dealing with all along. An ADT stands for abstract data type. Again, we've been using these abstract data types all along: queue, stack, list, all examples of ADTs. Next chapter, when we talk about trees, those are also ADTs. Container ADT that can be used to provide a queue based on a vector, list, or DQ. Very, very similar to kind of how we wrapped up the discussion on stacks. Has member functions to enqueue push and dequeue pop. To define a queue containing chars named CQ, based on a dequeue would look like this. Defining a queue with the default base container looks like this. Based on a list, you should be comfortable with this syntax now. So queue of chars, and we're going to use a list of chars as our backing data structure, again, noting the space between the greater than symbols. So recursive solutions to problems are often elegant but inefficient. A solution that doesn't use recursion is more efficient for larger sized inputs. Eliminating recursion involves rewriting the recursive algorithm so it uses other programming constructs like stacks and loops rather than recursive calls. And that may be record time here, 40 minutes. Let's double check. We finished up the presentation, but let's double check the text and make sure that we haven't forgotten anything. Here's their implementation of dynamic int queues. Of course, just like stacks, you can, and probably should, take the queue and templatize it, turn it into a template. Here's the use case for dynamic int queues. Here's the STL dequeue and queue. I'm hoping, yeah, the dequeue container. Just a few more words about the dequeue container. Think of the dequeue container as a vector that provides quick access to the elements at its front and back. Like a vector, dequeue also provides access to its elements with the bracket operator. So programs that use this class must include the dequeue header. Since we're concentrating on its queue-like characteristics, we'll focus on our attention on pushback and pop front. The queue container adapter, we kind of went through that in the slides, so there's an example. And then kind of a random topic here at the end, eliminating recursion. And that is going to do it. Yeah, non-recursive quicksort. Check this out if you're curious. This is a non-recursive version of quicksort using a stack to help you do so. A good example, I'll make sure to kind of go through this, scroll through this slowly, so you can feel free to both understand it and perhaps recode it if you desire. And that's it. Okay, that's chapter 19, which means we only have one more to go. Chapter 20 is all about the tree data structure. It's the data structure that I'm kind of the most interested in, I guess. I feel like it can represent the widest variety of problems and applications. So we'll get into the tree data structure in chapter 20. We'll close out the entire, basically the entire course with a few closing remarks, maybe some resources for further study, suggestions if you want to go even deeper in the language. But all that will be next time. We'll get into lesson 20 on trees. Thanks.